Hello, this is Professor Gutierrez, and we are looking at Chapter 5, Probability Distributions. Sounds good. In other words, the probability depends upon what you are looking at. What are the chances of getting heads? 0.5. Tails? 0.5. Now, that one's a uniform distribution, but we have other cases where it may not be a uniform distribution. Let's take a look at some of those. All right, probability distributions. The binomial distribution. That one's fun too. Poisson. Ooh. It's not poisonous, it's poison. All right, we're going to look at what a random variable is. Probability distribution, histogram. We already done one of those. We already did one of those. Did, not done. And decide whether or not something is significant or not. All right, random variable is a variable typically represented by x, because we like x. Single numerical value. So x can equal 4.5, 2.3, something like that, for each possible outcome. So if we're rolling a die, 1, 2, 3, or 4. If we were flipping a coin, heads or tails, we could say 0 is for tails and 1 is for heads, or vice versa. But it has to be a numeric value. Probability distribution is a distribution that gives the probability for each value of a random variable. This is best format as a table, formula, or graph. Formula if it's a bit more complicated, table if it's fairly simple, and graph if you get a graph. Two different kinds of random variables. One is discrete random variables. So these variables are either finite or countable. So finite means that you only have a finite number of them, and countable is a type of infinity. It basically means that you could act as if they were numbers, and you could assign them to numbers, to the integers 1, 2, 3, 4, 5, 6, and so on. Continuous have infinite many values, which are not countable, and the collection of values is not countable. And that's a pretty technical term, but yeah, if you're talking about like a function over the real values, that would be a continuous random variable. If you had one for each integer, that would be a discrete random variable. Every probability distribution must satisfy these three following requirements. 1, it is numerical, so like heads and tails wouldn't work, but you could say 0 for one of them and 1 for the other. The sum of the probabilities must equal 0, or close to 0 if you have rounding errors. And the probability of each item must be between 0 and 1. That makes sense. All right, 2 coins. X is the number of heads when 2 coins are tossed. So we could get 0, we could get 1, we could get 2. 0.25 for 0, 0.50 for 1, 0.25 for 2 are the probabilities for each one of these. With 2 coin tosses, the number of heads can be 0, 1, or 2. And if we add up the probabilities, 0.25, 0.5, and 0.25, we get 1, 1, and each of the values is between 1, and each of these is a numeric value, so it works as a good probability distribution. All right, and it's finite, because we only get 3 options. We can graph it. Number of heads 0, 25%, 1, 50%, 2, 25%. You can also run the You can also show the probability distribution to be in the form of probability of x is 1 over 2 times 2 minus x factorial, where x can be 0, 1, or 2. And it's 2 because we got 2 options. If we had 3 options, it'd be 3, 4 options, 4, so we shall see that. It's a bit complicated for us, but that is a formula that'll work, and we did learn it in the last chapter. So that will be important. Probability of 0, 0.25, 1, 0.5, 2, 0.25. Probability of 3, 0. All right, let's take a look at this. Job interview mistakes. Go to a job interview. You might make a mistake, or two, or three. I've made a few myself. Probability that you have inappropriate attire, 0.5. I personally thought the beer hat was a great idea. Being late. Fashionably late. How can it hurt? Lack of eye contact. I wore blindfold. Checking the phone or texting. Well, it was a phone interview, so that did not work too well. Anyways, what problems do we have? Well, number one, look at X. X is categorical data. It is not numeric data, so we can't use it. Next, P of X. Okay, each one of them is between 0 and 1. That's good. But if we add them all together, we get 1.53. And that is above 1. They have to add all together to give you 1. Do they? No. So this is not a probability distribution. Nope. All right, so if we have a probability distribution, we have a description of a population instead of a sample. So we have mean, standard deviation, and variance are parameters, not statistics. Mean, variance, and standard deviation of a discrete probability distribution can be found with the following formulas. Formulas we kind of already know. Mu is equal to sigma x times P of x. Okay. Remember, the big sigma, this thing right here means we're summing it. So for the heads thing, this would be 0 times 0.25, 1 times 0.5, and then 2 times 0.25. And you add those all up together to get your average, which will probably be 1, my suspicion. Variance, sigma squared. So again, little sigma squared, and then capital sigma, the sum of x minus mu squared times P of x. Right? And variance can also be written as sigma squared equals sum of x squared times P of x minus mu squared. So this one can work in calculators. These two will equal. I'm not going to go through showing why they're equal, but they are equal. So remember, variance is the square of the standard deviation. So standard deviation will just be the square root of that. The sum of x squared times P of x minus mu squared. Okay, this formula we will use. You will want to write this formula down. You'll also want to write this formula down. All right, these will be needed formulas. All right, we also have something called the expected value. What do you expect? What is your expected value? The weird thing about expected value is you may not ever get your expected value. So that is going to be the sum of x times P of x, and that's it. So let's say we tried to do that for a die roll. That's 1 over P of x for each, 1 over 6 for each one of the probabilities. So 1 over 6 times 1 plus 6. So that's going to give us 3 times 21 divided by 6 should give me, I'm just saying numbers. All right. It should give us about 3.5 as the expected number. And yeah, you're never going to get a 3.5 when you roll a die, but that will be your expected value. Right. So 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25. What do we get? P, x times P, which is 0 times that, 0 times that, equals 1. And x minus mu squared times P of x. You did write these down, right? Yes? Yes, good. Right. Plug these in here. Plug these in here. Plug these in here. And you should get this. And you should get this. A mean of 1, standard deviation of 0.5. All right. Not a standard deviation. My apologies. A variance of 0.5. Standard deviation is going to be about 0.7 because it's the square root of 0.5. All right. So these will give us our calculations. Mean 1, variance 0.5, standard deviation 0.707, which is just 1 divided by the square root of 2. I'm tossing 2 coins. The mean number of heads is 1. That makes sense. Variance is 0.5 heads. So we'll usually get between couple of standard deviations. So standard deviation is 0.7, so that means we should get 1 plus or minus 0.7 heads 63% of the time, which is 1 because that's discrete. All right. So we expect 1. Makes sense. Now, when we are looking at values that are significant, and keep this in mind, we're going to use this a lot. So we have mu, which is the mean. If we are 2 standard deviations or more above, this is considered significantly high values. If we are 2 standard deviations below or more, this is called significantly low. Otherwise, these values are considered just fine. Not significant. So we have 1 plus or minus 2 sigma, that would be standard, but that we would expect. So 1 plus or minus 1.4, so 2.4 to negative 0.3, I think. That just gives the upper bound 2.4. So everything we get is going to be expected. So this one is not that strange. Now, if we had 100 coins and we got 100 heads, that would be unexpected. And we'll start seeing some of the stuff like that when we look at the binomial distribution. Interpretation. Based on these results, we conclude 2 heads is not significantly high for the number of heads. And it's not. It's not an amazing factoid. All right, and this is telling a significantly high number of successes. All right. Again, not rigid. So why could we have a significantly high number of successes, or why could we have a significantly low number of successes? Well, one thing could simply be that, well, sometimes that happens. It's weird, it's confusing, but sometimes it does happen. Sometimes you do get 5 heads in a row. Sometimes you do get 6. You don't get 10 billion in a row, though. And it could be that a lot of people are doing it and you just happen to be the lucky person who got an outlier. Yay for you, depending on which direction your outlier was. And significantly low success. Alright, if, under a given assumption, the probability of a particular outcome is very small, your assumption may be incorrect. And that's how we check out assumptions. Make an assumption, we check it out. Does it work? Does it not work? Well, maybe we need to try something else. And the expected value of the random value is equal to the mean mu. You therefore find the expected value by computing this, just as we do for finding the value mean mu. Be a better. Who wants to bet? Who wrote this book? God, they just keep wanting to bet all their money. Okay, so we are gambling again. Be a better. Alright, if you bet $5 on the number 7 in roulette, the probability of losing $5 is 37 to 38, and the probability of making a net gain of 175 is 1 over 38. Prize 180. Including the $5 bet, so the net gain was 5. You find your expected value if you bet $5 on 7. Well, losing 5 means negative 5 has a probability of 37 over 38. And plus 175, 1 over 38. $5 on the pass line in a dice game, probability of losing $5 is 251 over 495. Clearly that, I don't care. Whatever. Probability of making a net gain of $5 is 244 over 495. So, I don't know enough about gambling to say anything about this. But I'm sure there are plenty of people who do. If you bet $5 on the pass line and win, you get $10, which means you get your $5 back and you gain $5. Find your expected value if you bet $5 on the pass line. Let's see that one. Well, this one's easy. Roulette. Event. You lose or you win. You lose $5 or you gain 175. Expected value here is 30, or probability here is 37 over 38. Probability here is 1 over 38. This is what you lose. This is what you win. Add the two together. This is your expected outcome. You expect to lose 26 cents each time. Now, that's an average. That's not for a single roll. So understand that you will not lose 26 cents for a roll, but on average, you should lose 26 cents per roll for the roulette wheel. Now, if you do the craps game, then same thing. Minus $5 is 251 over 495. Win $5, 244 over 495. Lose 250. Gain about 250. You end up losing a total of 7 cents per pass line pass. So that is an average expected outcome. You will expect it to lose money. Now, the reason you're expected to lose money is because the casino wants to gain money. That's why they're casinos. Right. Interpretation, don't gamble. But if you are going to gamble, pass line is a better bet. Or learn to count cards and then become a whale. Just prove me wrong. Just go to a gambling city. Nashville? Does Nashville have gambling? Wherever they have gambling, go there. Prove me wrong. Alright, that's what we got for section 1. Section 2 coming soon. See ya.